All right, great. So I gave this talk at Stir Trek in Columbus. That's a one-day developer conference. It's held in May. For anybody interested, it's a little bit Microsoft heavy, but there is a data science track. I think it's kind of interesting. The fun part of it, they do it at a movie theater, and at the very end, it's always timed with there's like a comic book or science fiction movie, usually in early May, and everybody has a ticket for that, and that's how you wrap up the conference and stuff like that. So the reason I explained though where I gave the talk, it is a little bit of a high-level overview, and so initially I was kind of concerned about that with this group because I go into some basics of RSyntax and a few things like that. But actually, this meeting in general, we had a lot of first-time attendees respond, so not bad to have some intro material in there. But the point is, you're not going to walk out of this, knowing exactly how to go write machine learning code. This isn't a tutorial. It's more of kind of a survey of what's available in R, what some of the concepts are, what are the things that you might have to do yourself, and what does R do for you, and what would it look like if it didn't do it for you. Feel free to ask questions along the way, or certainly afterwards I'll leave some time to take questions as well. Any feedback would be great. If there's things you think that weren't covered that should be, or things, I'm doing this talk one more time at a user group in September. So. Hold on here, if I can get, there we go. So for those new to the group who don't know me, I'm the organizer of the R user group. Jim Hester, who's here as well as a co-organizer. I am the Senior Director of Data Science at Dialogue Tech, and part-time, and I'm an advisory board member at a startup called Drive IT in Akron that does kind of after work, they do it like a gym-style courses for developers wanting to buff up on specific tools and languages. I'm T. Hoolihan on GitHub and Twitter. Isn't that supposed to, Jim, let me do keyboard? Let me try that again. Okay, now it's working. So agenda for the talk, we'll do a super brief crash course in some basics of R that help follow along for some of the code examples you'll see in the slides. Talk about what machine learning is, talk about regression or predicting continuous values, classification, which is predicting discrete or categorical values, touch on unsupervised learning, touch on deep learning, and then kind of where you would go from here with if you're interested in learning more. So I had to put a single slide, I figured, on our history here. So this is an implementation of the S language that has certainly evolved on its own and overtaken. I mean, S was a proprietary language. R is the by far more popular. Built-in support and strength for statistics. In particular, its package ecosystem is really what drives it as a dominant language in stats and a variety of STEM fields. Integrations with most major RDMSs, relational databases, big data systems, etc. So some unique things you'll notice right off. People notice that the assignment operator is a little funky. The bottom one is preferred and stylistically in R, but an equal sign is supported. But we'll make fun of you if you use it. Functions are declared through assignment, like the top statement. So those of you familiar with like JavaScript or something like that are going to be familiar with that syntax. Similarly, implied return is available. So the bottom statement does the same as the top. R has really strong support. Some would say everything is a vector. Vector is the preferred type for a collection. And so you think of it like an array or a list in a lot of languages. So right here I'm creating a list of height in meters. I can analyze or look at the length of that. Right away you'll see built-in functions for statistical type things in terms of getting an average or the standard deviation of those heights. One thing about vectors, the performance is a lot better when you use vectorized operations. And that is what we're doing at the top here in the line that assigns to temp, where you say heights times feet per meter. In a lot of languages, you would have to take the approach in the bottom. You would loop through that collection. That's very inefficient as compared to the upper way of doing it. And so as much as possible, you want to do operations on entire sets of data at the same time. I'll pause for a sec to make sure no one's glazing over questions. There's strong support for distributions and creating them in R for a variety of types. So here I'm creating a random set of data with a normal distribution. So 500 observations. I'm specifying that the mean of those observations is going to be 66, standard deviation of 3.5. And I've indexed the array, which is just give the first 5 values as an example there. I'm using a normal or Gaussian distribution there, but there's all kinds of functions in R for various different distributions that you'd be looking for. They're built right into base R. Plotting is a first-class function in base R. This is a simple histogram function, so I can confirm that in fact that data I created does have that familiar bell curve that you would expect of a normal distribution. So we're going to take that first variable and create a related variable. So if you remember your Da Vinci picture with the circle around it, your arm span is actually roughly your height. And so, but here we're just giving a little bit of variance to that. Obviously it's not an exact measurement. And so, again, this kind of combines a couple things we've seen before. So this time, instead of a normal distribution, you'll see the RUNIF. That's not run if, that's random uniform distribution. So 500 observations between -3 and 3, and they're going to be completely random. So uniform distribution, not Gaussian. I'm adding that, we talked about vectorized operations, to heights. So I'd have to loop through and create a new variable each time. I just created 500 observations, and I'm adding it to height. And now I have a new vector, which is arm span. So arm span and height are the same length, right? Because obviously we're going to line those up. There we go. So when I say line those up, you might think of like if you're working in a spreadsheet world, you put those pieces of data into columns. In R, we use a data frame for that. It's a table-like structure, has rows, columns, and you'll see here that I'm creating a data frame. I can name those columns with the parameters as I pass them in, height and arm span. And I'm using the head command. Head is for those on Unix, you probably know it's first 5, or actually 6 in this case, rows of something, but, you can often use that at the shell if you're looking at long text files. In this case, we're just truncating the data frame, right? So it doesn't print off the page and those type of things. If I look at the dimensions of that data frame, I'll see that there's 500 observations of 2 variables, is sort of the way you would read that. I can index it in R a number of ways. The $sign allows me to go data frame $column. You'll see the height there. I can look at an individual row with that numeric index, or I can look at both to get down to a specific value. Sorry for the long-time members who are sleeping through this. I promise it warms up a little bit soon. So we'll bring in ggplot2 as a more modern plotting library. This is part of the Hadleyverse, what's the real name for it? Tidyverse, thank you. But Hadley Wickham that works at RStudio, one of the packages he and others helped write that does a more attractive and modern job of plotting than the base R packages. So if we want to start analyzing this data, we can do a quick plot and have height against arm span. And as you'd expect, right, there's this strong relationship together, right? But a wide band, and that band comes from the random uniform noise that I added to it, right? One thing to point out here syntactically, notice that we didn't have to say people $height when passing it into the plotting call. We say data equals people, the data frame, and then it's using that data frame to resolve all the arguments. You'll see this convention in a lot of R code, and those of you in R would even wonder why we're pointing this out, but other languages, this is not a common feature of the language. And so certainly with pointing out to new R users coming in, you would expect referencing like a property on a class in another language without the object to not be something that resolves with syntax. But that's not an issue here.
Basic question. Is this because ggplot is set up this way? Because in most R functions, at least the one that I use, I still have to put $sign this, $sign that. It becomes much longer. So I don't know if this is only for ggplot. It's just set up that way.
Yeah, the function signature has to be set up in a way that it's going to handle that. I forget the exact mechanism. I've written this before, but is it something easy to describe, Jim, or is it easier to show later?
Yeah. So this technique's called non-standard evaluation, and basically, you evaluate the arguments in a different environment than you would think. Like it takes another parameter of the function call and evaluates them in that environment. So that is definitely a property of like the function. The function has to be written with this technique. So yeah, it definitely doesn't work for anything.
Yeah.
So when you do data equals people, you can use the height and the arm span without the $sign, but you can't use tab. So if you use attach, then you can use tab. But some people don't like to use attach. What's like commonly done? Because my variables are normally not just one word, so they need to sit there and type it out. But if you have the tab,
Gotcha.
fills it in and then
You're talking about white space within the.
No, I think she's talking about autocomplete.
Yeah, autocomplete.
Like
Oh.
completion.
You have to attach
So-
it though. You have to attach it set.
So at least in RStudio, a lot of the time, like there's somewhat smart auto-completion, so it actually will take into account the variable and auto-complete the variables. But yeah, that's not, and that's only for certain functions. Like I think ggplot might do this, and dplyr definitely does for sure, but not every function is going to have that.
Yeah, I was going to pull up an example, but I forgot I don't have this kind of queued up where.
yeah, if you attach the data, then you can auto-complete your variables, your features, which is convenient. But some people don't like to use attach. You have to be very careful to detach it. I don't know if there's another way to use auto-complete of your actual variable names.
Yeah, I'm just used to RStudio generally handling that. Like I'm in other environments, I'm not sure what alternatives to attach you would have. Yeah, I don't know if anybody's got R up and wants to play around with that and answer later, that'd be good. So if we're going to look at the relationship between those variables, there's a function for getting out a linear model from that, LM. And that uses a formula. So this is another RSyntax feature. The arm span tilde height, you can sort of read that as arm span by height. So a number of places where you're doing plotting or comparisons or modeling, I want to look at the first thing. I'm specifying that arm span is the response variable, and then after that I'm listing the features that I'm going to use to make that determination. So in this case, if I look at a summary of that item that comes out, the important part here, you look at the coefficients, and so you'll see there no, I'm looking at importance there. Hold on one second. Yeah. So I'll come back to that. So I can look at a general summary of the model, and that'll give me some information about both how important the intercept is, how important the height is, and you'll see obviously I have one feature here, so it's pretty important, and it directly correlates. So not surprisingly, that has a high correlation. So the last, you're getting t-values and p-values in terms of association. In terms of what the actual coefficients are, if I look at that out of the structure of the model, I can see that the intercept is 0.25 and then the height here at 0.99. So interpreting that right, if you remember your y equals mx plus b from high school, whatever, we'd look at that at the bottom and say the arm span is that 0.9956 times the height plus the intercept of the 0.25. So if we apply that to our entire data set, then we're able to get a line to say, based on that model, where would the expected arm span be through the height? We're not even really doing machine learning or prediction yet. The point is to take that. Now if I plot and I add that as a line, I'm just seeing a regression line through the values. So it's that bottom line that adds it to the original graph that we built, right? So what is that regression line, right? I mean, it's a pretty straightforward concept that most of us learned in one form or another, but it describes a relationship between the response variable and the dependent variables. In other words, how arm span is going to change as height changes. Notice that we didn't create that by writing procedural code and describing a relationship. That model was created by inferring the relationship from the data. Does that make sense? The reason we sort of highlight that before I move on is because essentially that's the core of the definition of machine learning. And that's to, as opposed to sitting around and pontificating, well, what might this variable do for this variable? It's giving an algorithm. So a structure, you're still selecting a structure. In this case, we're selecting a linear model, that y equals mx plus b. But we're giving the algorithm that creates that a bunch of examples and letting it learn what the relationship is. So a key question is, does that relationship hold? And so I made up this data in R, but for argument's sake, we're saying that that's American adults age 18 to 50 measured in the last 10 years. So you can start to ask these questions of, is it valid in France? Is it valid for children? Is it valid for senior citizens who are outside the 18 to 50 age range? Is it valid for ancient Neanderthal people, etc.? So you said we're not programming rules, we're inferring patterns from data. So I won't read that line by line, but the point I get to at the bottom about that, where it should be applied, as an example, probably shouldn't be applied to children, right? All our examples were adults. So that relationship may or may not hold for children. Similarly, I would sort of question the Neanderthal or the different age range or whatever. There's no necessarily right or wrong, but the further you get from your training set, the less likely it is that your algorithm applies. So how do we use that to make a prediction? In R, the predict function takes a model of most any type and any kind of new examples, and then gives us a response. And you'll note here I use a list as opposed to, since we're just doing one value, there was no reason to create an entire data frame. Those structures work as well. But if I had passed in a data frame of multiple values, I would have gotten multiple predictions. So before we jump into some more traditional machine learning examples and things, just a couple quick words on definitions of data sets, because you'll see here referring to training data sets, validation data sets, testing data sets, and whatnot. So the training data set is the data that we've chosen to give to the algorithm. So in supervised learning, which is meaning that we are giving data that has some sort of an answer and we want to predict that answer, training data has to be labeled, has to have an answer, and that's the data that we're going to give to it. So we used only training data in the contrived regression example that we started with, because we gave the entire data set to the algorithm to create the regression line. Validation data is data that you're going to hold out of the training process to regularly use to check the training. That might change each different time you do training. There's a variety of techniques for selecting that. You're going to be tinkering with your model, working through the process iteratively each time you have training data, and then some of it that you hold out as validation data. And the idea is it's not very hard for the algorithm to predict on a record that it's seen. We want to see how it does on records it has not seen yet. And the ultimate example of that is the test data set. So that's held out until you are ready to publish your model out to a production system, and that is going to be your best prediction for what will this work like in the real world. Even though you're holding out validation data while training, that informs the tuning and iterating you do, so it has a chance to bias the model. And so to get the truest measure of how the set's going to perform, you want to do that. You want to have a test holdout set data. For anybody who's gone to some of the local user groups that do Kaggle competitions, or you've just signed up on Kaggle and gone through an exercise, you download a data set, you're going to split that into training and validation data while you're working through it. The leaderboard data that they give you that you don't have the answer to, that's the test set. And you're not supposed to have the answer to that. That's how they score you versus other people. So most machine learning in R outside of deep learning is going to be done inside the Caret package. It's really, this is the name short for classification and regression training. It's not really so much a package of machine learning as it is a superset of a bunch of packages of machine learning, kind of a wrapper and an interface for quite a few modeling packages. So in addition to wrapping all those modeling packages as a number of helper functions for things that you'll do along the way when machine learning. So data splitting and preprocessing, feature selection, model tuning, and variable importance estimation, amongst many other things you can still do in there. Yeah.
Hi, Tim. Hope this question is appropriate. I'm not really sure if you're looking for more, advanced questions, but in the previous slide you mentioned that machine learning is used to infer a relationship. Do you think it might be a little more accurate to say to infer a certain type of relationship? Like, for example, linear regression versus nonlinear regression?
Yeah, yes, within the limits of the algorithm you're using.
I mentioned that because some people might get the impression that you just give it data, that's it, and it's going to find a relationship. But to a certain degree, we're telling it what type of relationship.
Correct. Now there are techniques like, and actually Caret has the ability to take like a number of classifiers and iterate through them, where you can even maybe infer the best technique. But yes, within that pattern is going to be within the structure of whatever model type that you've selected for it. That's a good point. So looking at regression, similar to what we did before, but within the context of Caret, we'll use the MT cars. This is a motor trend car data from like 1976, I believe. So a built-in data set to R, which, going back to actually talking about features that makes R nice to work with, there are kind of a number of these toy data sets built in, and then additional packages. We'll look at one like ML Bench later, that when you bring in the package, it brings in data sets to work on for practicing the craft of doing this. So if we just select these 5 variables, so horsepower, miles per gallon, displacement of the engine, weight of the car, and the quarter second time, and give that as our X data. So we've just limited it down to, for simplicity's sake, some continuous numeric variables. So one indication to know whether our variables predict well is to look at the correlation of those variables. And so R has a nice function called pairs that's going to put out a correlation table. So we'll be predicting horsepower. So if you look across that top row, you would see horsepower versus miles per gallon, horsepower versus displacement, weight, and quarter second time. And the good news is, we ought to be reasonably confident that we have variables that are useful, because most of them look like you could draw a fairly good line through them to describe the relationship between the two. So we'll load up the Caret package, and we're going to create a training set. And I kind of made the mistake of calling it a test set. Probably should call that a validation set for my definitions earlier. But the function we're using on the first line, create data partition, is a Caret function. So one thing to note right away is that I have not passed it the entire data set. I've passed it the column that we're going to predict. The reason you do that is that it does what they call a stratified sampling. And the idea is that it's going to intelligently distribute out the records and randomly select to try to have, the idea would be in the way of horsepower here. If we just took a random sample and ignored the column that we're trying to predict, it might be that random set that we select ignores all the high horsepower cars, right? And now our model is going to struggle in that area. So this create data partition is going to look and see, okay, do the distribution of horsepowers in the training set match that of the test set? The P equals 0.7 is saying how much data do I want in each. So I'm doing 70% for test data. And list equals false is an annoying default for this that you're overriding that in order to be able to use it as an index. So one nice feature R here, you'll notice where I'm getting the data that does not match the index, I can use a negative index. It's kind of cool. I think a lot of other languages could benefit from such a thing. So if I look at the dimensions of my training data, I see I have 24 observations of 5 variables. It's pretty small. Again, this is a toy data set. To create a model in Caret, use the train function. So here we're doing horsepower by dot in the formula. That dot is a shortcut for everything else in the data set that we've passed in. The data argument in this case is the training data. So that's been subsetted by that index I created. And then I'm saying that the model I want to create is LM. So behind the scenes, it's using that same LM function that we were using before, but this is wrapped in an interface that is uniform to Caret. And the nice thing is I could change that method out to a number of other regression models by just changing that parameter. We look at a summary of the model. You'll see, again, your measures of importance of each of those variables. In order to predict that on the test data set, so here you'll see instead of a single example like we did before, we're passing in the whole test data set. I'm capturing that as the column predicted, just so that we can do that as a comparison. And then I do predicted minus horsepower, so you can see the difference here. I think for Cleveland folks, I should name that the diff for you Cavs fans. But then the idea is we can output the data set with the horsepower, the predicted, and what the delta is. Yes, question?
Question on that. Actually, in previous slide it shows some p-values, right?
Mm-hmm.
how that p-value will support the prediction?
So that's just going to give you, you're using that as a correlation measurement as to whether that what is it technically, stats folks correct me on this because I'm more the engineering side, but it's the probability that is that the association found between the two is meaningless. And so the smaller the p-value, so this is just going to be the idea is going to say within this model, just this model, not necessarily all other models, but within this model, this is the amount of importance of that variable versus the other variables. It's not a value that's directly used for prediction. More the result of that would be if I were to pick my worst one and drop it out, right? Then I've used that feedback to tune my model and say, okay, this variable, there's too much of a chance that this is an unimportant noise variable. Let's see if it models better without it.
So is there a way to automatically drop the insignificant terms?
So there's, what is it? K-best is usually where you give it a number, you say, I want this many columns, and it will automatically figure out and choose the best within.
Yeah, but the right way to do is to take the worst p-value, drop that one, rerun the model, drop out find the one with the worst p-value.
Stepwise or backward selection for model selection. Yeah, you can do that.
You can.
I know how to sass it. I don't know how to do it in R.
I was going to say, when I've done that, yeah, I just haven't had it come up in R. I've done it within Python with K-best. I don't know if that walks through the sklearn, if that does it iteratively, or if that does it, I'd have to look at the implementation.
There's several options. So I'm a statistician who knows something about R, but not it's statistics then too. First thing I'd say is, if you actually care about the answer, you probably don't want to use significance tests to make the decision in the first place, and you definitely don't want to use backward selection if you want to get a right answer, if there is one. But that said, I understand you've got data, you got to do something. There are stepwise methods in R, both for just pulling out of a linear regression or other tools like more generalized linear models. And there are tools in R to do best subsets of various types as you describe in there. And if somebody cares about it, I can try to throw something together and give a talk sometime, I guess, about it. But they do exist, but inevitably what you're going to want to do, best practices if you're doing that is to then validate that result anyway. So there's a limit to how much additional gain you're going to get from implementing that step within the training that you're doing here, because you're just going to test it the way you test it to get something you can actually believe in for prediction. I mean, this is different than I'm trying to decide if this is statistically significant enough for some other reason. I'm just assuming that what we want to do is get the best possible predictions.
Yeah.
Anyway, the tools are there. They do exist.
I mean, if the best model is the simplest one, why wouldn't you want to drop the insignificant terms?
You just wouldn't want to use significance to make that decision. Whatever the best model is, I'm thinking in terms of it's the one that does the best job at predicting in your data, and significance and that aren't the same thing. That's all.
You're just saying empirically test it.
Yeah,
See
I'm
what's,
just saying if you're going to do
Yeah.
it, then you're going to want to do it empirically. If your goal is prediction as opposed to like explaining that quarter second time is really important and
Yeah.
G isn't, I mean, if your goal is that, then it's different, of course.
well, and obviously, you sort of have a choice between feature selection and you could do dimensionality reduction too in order to reduce noise as well. We covered that already. So measurements of error, there's a number of packages for getting out. So this is mean squared error. I'm using the model metrics, and I believe it's mean average error. In general, obviously you can sort of question the interpretability of those. That's just going to sort of be a comparative metric that you as you model, you're looking to improve over time, right? A applying that to a sort of a non-toy, stepping up a little bit. This is a Kaggle data set of housing pricing data. And so in this case, we've got 1460 is the number of observations and 9 variables. I pulled out some continuous and a few classification variables. Wanted to show dealing with categorical variables in a linear model. So in this case, we've got neighborhood, and that's a factor. So factors in R are discrete values. So we've taken those strings and converted them to, in other languages, you can sort of think of it like an enum. So like there's an index behind the scenes that's being used to look up that value. So R knows there's only so many neighborhoods, and it's able to process those a little bit faster because it's not treating them as strings. It's treating them as individual discrete categories. To walk through this example, we're also going to use cross-validation. Cross-validation is one of those things that, like, once you've done it and sort of understand it, it's fairly simple describing it. Like, this was the best visual I could find, and I still sort of hate it. But the idea is just that as you iterate through the data, each time you're going to select a different holdout validation set. And you're just doing that same process, rinse and repeat of that. And that allows you to train on all of your data, but on each of those iterations, get a score of data that was held out. So you're still having the benefits of a validation data set, but it's something to do when you still wish you had more records. I mean, if you have millions upon millions of rows more than you need, it's usually simplest to just do a stratified split and then be done with it. But having enough data is almost always a problem.
Is there some way to know when you have not enough validation data?
I mean, I don't know of a definitive way to know that. I think that's more of based on experience and results of, if you're getting wildly different results on your test set than you were on your validation set, then likely you're not using enough validation data. So doing cross-validation in R, we set up this training control object, if you will, with the train control function. So we're telling it here we want to do cross-validation, in this case using 10 folds, and saving predictions just means that it's going to keep those predictions as it does the iterating through and selecting different sets in the background, so we can actually take those predictions and apply some metrics across it and see what our validation scores are. In this case, I've just happened to pick another regression model just to show how easy it is to swap out. You'll see the method equals lasso there for lasso regression. And the bottom, I'm doing some pre-processing. We'll touch on that in a minute. Again, just getting out a standard metric here for the, so you see the model predictions. It's kind of awkward syntax, but that's how you get to those saved predictions for the cross-validation. So I centered and scaled the data. A lot of these algorithms, particularly the linear ones, are more efficient when your data the features are roughly equivalent in terms of scale and range. And what I mean by that is, so with housing prices, square foot of the house is going to be a number in the thousands. Number of bedrooms is a number, 0 to 10. That's very different range of data. And so oftentimes for algorithm efficiency, and you'll see the data centered and scaled. So in case of centering here, what we've just done is shifted it. So I took the value 0 to 10, I center it, you see the result is it's now -5 to 5.
That's sort of the same thing as normalizing the data?
Yeah. So scaling, here we're just changing to a range of 0 to 1. So, so the largest maximum value that that the scaler has seen is going to become 1. The minimum value is going to become 0. If you applied both of those, then you see, you know, a large, I've got a random uniform of, what is that, 1 million to 10,000 to 5 million, and I center and scale it, and all values are between now negative 0.5 and positive 0.5. Obviously so you're gonna, once you've done that, you've got to save the translation, if you will, for that, or transposition of those numbers per column, because that's going to be different for each column. Caret handles all of this for you by just building it into the model in the pipeline. So when I say preprocess is center and scale, any new data I run through that model is going to be centered and scaled with the same parameters that were determined from the original set. I'll touch on missing data. This is kind of a big topic, so I just want to point out that this is available. There are functions in there to help you impute missing data. This particular one is going to use k-nearest neighbors to look at other features that are present and say, okay, for this missing value, I'm missing the number of bedrooms on this house. What's the most likely number of bedrooms based on houses that look like this in terms of square footage, other things like that. There's a number of different ways to fill in missing values. That's just one of them, and it's available there pretty easily. So jumping into classification, this is where we're not predicting a continuous value, but some sort of type or discrete value. And so when I did the talk in May, everyone was watching the Avengers afterwards, so I used the examples here of comic book classifications. So if I've got a list of the actual at the top and then the predicted, one way to compare that is to create a table of them. The values that are correctly predicted, right, are along the axis, the diagonal, right? You'll see cannon fodder, hero, hero, that kind of thing. And so it's a quick way to visualize the predictions and see, okay, anywhere that I've missed the axis, that's a missed prediction, right? And so in larger data sets, that kind of becomes a heat map for what kind of problems you're having in your model. So for this example, we'll use the iris data set that's built in. So this is about iris flowers. Gives you a variety of attributes to it, and then a species. The species is a factor or a class. And we're going to do cross-validation. And in this case, we're doing a radial support vector machine as the algorithm, and just scaling the data. Now, Caret has a confusion matrix function built in, which adds a few other pieces of data to it. It will give you F-scores per category and some other things. But if you ask for the table, you'll just see a table like I created before. And so in this case, we'll see that our algorithm, just at first glance is doing pretty well. That 147, 140, 141, those are all correct predictions. And so there's 22 in correct predictions in that case. So not too bad. And you can see, so prediction is labeled on the left. So reference meaning the actual answer is on the top. So at times, you can extract other information out of that, like the last column, Virginica. You'll see that when you're misclassifying it, you're only misclassifying it as versicolor, not the setosa at the top. If anyone's a botanist, I'm sorry. I probably just butchered those names. Something I did there, I noted in a comment above, but I wanted to point out, again, for anyone new on the R side, I actually prefixed the function in this case with the package name. So you'll see the caret : confusion matrix. In this case, I actually had to do that because the model metrics package that I loaded up earlier also had a confusion matrix function. And so to be explicit about which one I wanted, I prefixed with the name. In some cases too, it's just nice for code clarity. If it's kind of non-obvious where a function comes from, you can just do that to be explicit so anybody reading your code knows where that's coming from. So I did that in one more slide to sort of make that point of if you weren't as familiar with variable importance as a function, reading this you would know where it came from. So this is built in, before we had our discussion about what was looking at the summary of the model and p-values and those things. Caret has an additional function for giving out variable importance that describes is using the receiver operator characteristic. Just different way to look at which variables are worth selecting. Unsupervised learning. I believe we have a video up of Brian Lewis's talk on clustering in general, and I think that's a really good deeper dive into this, but we'll kind of briefly touch on it. Unsupervised learning is really more of just an exploratory tactic to understand a variety of things about your data. So in this case, we've gone back to that empty cars set and plotted on the left plot. That's, apologize, it's not coming out very great on the font size there. Horsepower on the bottom axis and quarter second time on the y-axis. And then the colors are by the number of cylinders in the car. And so you can sort of see some clusters there. And if we project that down to one dimension, using something like principal components, then you can either be more explicit as to see how well those clusters sit together. In 2 dimensions to 1, that's not really necessary, right? Because we can see the 2, but the reason that we show that here in 2 dimensions you can visualize is to say that when you have 15 features, unless you have evolved more than I have, you can't see in 15 dimensions. So until you cluster down to at least 2, you're not going to be able to look at this data. And so with that in mind, the idea, you cluster and look at your categories, you can begin to see, okay, are these useful features to get to separating these categories? Put another way, so like we do in our work, we use transcription data and a lot of natural language processing techniques and try to automatically categorize calls based on them. And one of the first things we do when we determine the categories is to do some dimensionality reduction and then T-SNE clustering and then color the whole thing by the categories. And just see if 2 colors are completely overlapping on that chart, then we know, okay, they're going to be more difficult to model against each other. Whereas if you have nice clear patterns and separation, then we're optimistic about the job we have to do. But you might say, what's the purpose other than that optimism? I mean, in that case, you might actually go back to your stakeholders and say, these categories are going to be challenging for that. There may not be information in the data that supports it. Can we look at combining or separating these categories or some other meaningful technique? So to look at an example of this, we'll load up satellite data. This is coming from the ML bench package. So this wraps a number of data sets that are useful for machine learning benchmarking and just general machine learning practice. There's about 6,500 records, 37 columns. This is a particularly useful technique because this data is not very interpretable. So these are, I forget if this is either an image serialized out or if this is sensor measurements or whatever. You could go look up the data set help, but the point is all of these columns have non-descriptive names. They're, let me see if I somewhere show them. I don't, but regardless, the point is they're all continuous values. There's going to be no looking at that data and trying to interpret what it is just with your eyes and your brain. You're not going to make any decisions about features from that. So you have to use a technique like this. So yeah, so I'm looking at an individual column, but they're all roughly like this. The minimum value there is 27, max of 130. This is just a continuous spread out set of data. The prediction, what we're looking at is labeled classes, and this is what the satellite's actually seeing. So it's classifying into these different types of soil or crop. So it's real simple. The X data, the features that we're looking at, is every column except the last one, and that last one is in classes. That's our prediction or response variable, excuse me. So if we want to do a visual cluster of that, we're going to do principal components. And in this case, I've selected just 2 components so that I can plot them. And I'm just putting out the data at the bottom there, so you'll see that's transformed down into the most important 2 components, and I'm seeing the type. And if I plot that and give the colors to the plot, then you're able to look at that and see in general they're pretty separable, right? And you can actually pick out things. So I believe that's kind of a purple color and the blue that you might look at and say the blue spreads out further, but where the purple is within the blue. That could be problematic, those 2 classes. That's very damp gray soil and vegetation stubble, which actually even kind of makes sense when you think about it. But so that's an exploratory technique to look at that. One syntax thing to point out before we move kind of into the deep learning section is the pipe operator. So you'll see this a lot in the tidyverse, and that is an operator that allows you to nicely chain calls together. So it's going to take whatever's left of the pipe operator and pass it in as the first parameter of the next function that's to the right of it. So these 2 statements are equivalent. That example is contrived and it looks sort of awkward, but the point of it is for things like this. So this is dplyr, one of the packages in the tidyverse that's doing data selection and manipulation. And so I start with a set of flights data. I'm grouping it by the various columns that have to do with the date, selecting which columns I want, doing some aggregation and filtering. And so that's clearer than just having to keep assigning to some temporary variable and then having a new line through it. Kind of has a nice, almost SQL-like flow to it, right? And we point that out because that's used in the Keras implementation within R, and so there's a fair amount of code here. Again, this is not a tutorial as much as a survey, but we're going to use DNA data, and this is going to similarly, let me just run some of this to show you the data. I sourced the whole file. Hold on. So you'll see very sparse data here, right? And I mean, again, completely non-interpretable, high dimensional data. So an interesting fit for deep learning, right? But what we're trying to actually extract out of the data is going to be the class. And I forget, you can look up what the different classes mean, but obviously somebody in genetics would find this important. We split our data, and then here's where that syntax comes into play. So we're not, I'm not sure if there's Keras helpers for Caret. There was not as of when I first started working with the Caret package. It may have been wrapped since to be easier to work with Caret, but it's not difficult to work with Keras directly. And so we're starting off with this sequential model object and then adding our layers each time with the shovel object, the pipe operator, excuse me. And so that keeps us from passing in model each time into the function to keep building up. So you'll see this is a hidden layer or initial layer with 180 is the number of output nodes, for those of you who know about neural networks. Got an activation function, we're using dropout. Those are kind of advanced deep learning concepts I'm not going to go into here, but let me show that running. And why it runs, we'll talk through. So it's nice, you get the visualizations here of loss and accuracy as you go through. For those familiar with TensorFlow and Keras, those are both Python packages, but they've been wrapped to work with R. Really nicely, the work they've done to marshal the data back and forth is impressive. There really is not a large performance hit. If this was a machine with a GPU that was capable of being used with TensorFlow, then you would get the GPU optimizations of that package. For deep neural networks, that pays off a lot in terms of speed.
What's the size of this data set?
DNA is... Yeah, 3,000 records, 181 rows. So that's one of the reasons that I was able to, it actually did 100 epochs through that, so it's iterated through it 100 times. If that was a very large data set, on this machine, I'm using CPU only, so it would have gotten fairly slow. Yeah, again, deep learning obviously is a big topic. There's entire courses, books, things dedicated to it. The point here is just to show that is possible in R. One of the logical questions though that comes up with that, like with Python doing it in the background, people will ask if you should do that in Python or in R. It really depends on the context of your team, your project, all those different things, right? If you're an R-based team and you have a lot of existing code in R and analysis and you're just down to the final modeling point, and this works for you, I think that's a better solution. If you're starting from scratch with a team that knows both and you're just going to be focused on deep learning, I would say why add an extra layer to it in terms of the language? I would just work in Python and go from there. So again, it just depends on your use case. So we didn't touch on or barely scratch the surface of most of the things that you actually do to build really good models, right? We build a bunch of toy models and simple things there. Talking about feature selection or dimensionality reduction in terms of both getting noise out of your data, but also making the compute time quicker. That's pretty key. Dealing with missing data, right? All these data sets that are loaded up are friendly data sets that are not missing values. That is often not going to be the case in the real world with data. And you have to think about how you're going to deal with that. Model tuning, could do a whole talk just about hyperparameter tuning, which is of a lot of these models, I just let all the default parameters go in. For example, a lot of algorithms have what they call a learning rate, which says like how much they're going to adjust the weight each time as they iterate through and do that. Those are values that need tuned. Again, that's a kind of a specific technique and something you're going to learn as you really try to focus in on building better models. Algorithm selection, right? Like per Joe's point earlier, the algorithm sets a structure for how you're looking at the data. If you have linear data, a linear model is going to be pretty successful at it. There's a lot of data that is very nonlinear, in which case you need to look at other algorithms. And there's a lot of material out there about how you both think about and intuit that and how you empirically test that. Lastly, just the entire field of statistical learning and there's a number of techniques from, if you look at the books like Elements of Statistical Learning, Intro to Statistical Learning, there's techniques in there that have been around in the modeling field for forever that are still valid in machine learning and should be brought in. And None of that belongs in a survey talk, but the point is that there's a lot of places to go from there. So for folks looking to get started in machine learning, a couple of places to jump off. The Coursera machine learning course by Andrew Ning is sort of a very popular of the online courses. He's since added, I think, a series of 5 courses that walks you through from traditional statistical learning to deep learning. The Kaggle.com forums and tutorials, very effective. Takuya, that often attends here, runs the Cleveland Data Science Group. There's a longer name to that, has all the like R, Python, Julia data science group. They meet a lot of times on the weekends and will pair up on Kaggle problems. That's a really useful way to get started. I have a setup that goes into a little more detail, some videos online of techniques for this. And the slides are up on GitHub. All right, thanks everybody for coming. And remember, looking for speakers. Looking for speakers.
Oh, fine. Work micro. It was a very interesting topic. What I did here. Were you recording it? Is it online?
Yeah. So I'm gonna stop.